Why is it that certain diseases, like COVID-19, spread so fast while others seem to just die out immediately? In this video, we will be going over the math behind disease infections.
Let's begin with a simple population. Blue dots are healthy people who could become infected. One person enters the population carrying a disease. That person meets other people. Some contacts do nothing, but occasionally the infection spreads. One infected person creates another. Then those two people can infect others. At first, the numbers are small, but every new infected person creates another opportunity for the disease to spread. So the important question is not just whether the disease can spread, it is how quickly new infections are being created. A simple epidemic model divides the population into three groups. First, there are susceptible people. These are people who could become infected. Then, there are infected people. They currently carry the disease and can spread it to others at all times. Finally, there are recovered people. They are no longer spreading the disease and, in this simple model, cannot immediately become infected again. People move through these groups over time. Susceptible people become infected, infected people eventually recover. So, an epidemic is really a competition between two processes. New infections are being created, but infected people are also recovering. The entire outbreak depends on which process happens faster.
This is where differential equations come in. A differential equation is just a simple equation that gives rules for how an object is moving at a certain time. For an epidemic, you can think of a differential equation as a number of infected people and how it's changing at a current moment.
That change has two parts. New infections increase the number of infected people. Recoveries decrease it. So, the basic idea is the change in infected people equals new infections minus recoveries. In the equation, beta represents how easily the disease spreads. Gamma represents how quickly infected people recover. The term involving susceptible and infected people measures how often those two groups interact. The more susceptible people there are, the more opportunities the disease has to spread. And the more infected people there are, the more sources of infection exists. The equation may look complicated, but it is only keeping track of a race. Infection versus recovery. Now, imagine that infected people recover fairly quickly, or perhaps they do not meet any other people while they are infectious. One person gets infected, they may infect someone else, but before the chain grows, people begin recovering. The red group rises slightly, then it starts shrinking. Every infected person is creating fewer than one new infection on average. That means the disease cannot replace every person who recovers. The outbreak runs out of momentum. A few people may still become sick, but the chain of transmission eventually ends. The outbreak fades away. Epidemiologists summarize this competition using a number called R0. It represents how many people one infected person infects, on average, in a fully susceptible population. If R0 is below 1, each infection creates fewer than one new infection. The outbreak shrinks. But if R0 is above 1, each infected person creates more than one new infection on average. Now, the outbreak can grow. That number, 1, is the tipping point. Below it, infection chains tend to disappear. Above it, they multiply. And the difference between the two situations may be surprisingly small. An outbreak with R0 equals 0.9 may fade away, while an outbreak with R0 equals 1.1 may continue growing. The disease barely changed, but mathematically, the system crossed the threshold. Now, let's compare two populations. Both begin with one infected person. In the first simulation, the transmission rate is just below the tipping point. A few infections appear, but recoveries catch up. The outbreak disappears. In the second simulation, we increase transmission only slightly. Now, each infected person creates just over one new infection on average. The early difference is almost invisible. For a while, both outbreaks look small. But then, the second outbreak begins accelerating. More infected people creates more opportunities for transmission. Those new infections create even more infections. The result is a wave. A tiny change in one parameter produces a completely different outcome. But even when an outbreak grows, it does not grow forever. As more people become infected and recover, the susceptible group becomes smaller. There are fewer people left for the disease to reach. Eventually, each infected person begins creating fewer new infections. The outbreak reaches its peak. Then, recoveries become more common than new infections. The infected population starts falling. The wave collapses because the disease is running out of susceptible people.
So, an epidemic does not grow simply because the disease is present. It grows because the rate of transmission is greater than the rate of recovery. Below the tipping point, an infection just disappears. Above it, though, it multiplies. And that is why two outbreaks that can begin almost identically can have such different outcomes. One may grow while the other one may just fade away. That difference may come from a very small change. But once a system crosses a certain threshold, their outcomes can be drastically different. And that right there is a differential equation behind an epidemic's tipping point. I'm Lucas Zelensky, and I hope you enjoyed this video. Bye.